Okay, I think we should start now. It feels that most of you are coming to the same school bus. Okay, so this time we will talk about something very much related to how we model the Earth system, and particularly how we model the atmosphere. So we talk about approximations first. Why do we do approximations? Last time we talked about this, right? This is one of the reasons, not just to save computer resources, right? We want to filter the signals that we don't want. For example, if we want to do simulation for future climate, then we don't care about the sound, right? The sound, the audio signal in the atmosphere. So we do some tricks to different terms in your equation, and in order to remove some unwanted signals. Of course, that leads to some errors, and we will have to bear that in mind when we do assumptions. Okay, so this graph is showing you different things in the atmosphere. So a lot of things are happening in the atmosphere, and they should be in different scales. And by scales, we are talking about spatial scales. So in space, right? The x-axis here, and the temporal scale in time. So you can see that the Mother Nature is very nice to us, right? Most of the weather systems, they are lying on the same plane, right? Same area, same regime. So the things that you see, extratropical cyclones, so the winter storms in the US, or mesoscale processes, for example, thunderstorms, or squall lines that we have in Hong Kong, or tornadoes. So different things, and even tropical cyclones, they are lying here. They're related to some atmospheric waves. So that's why they're lying here in this regime. So there are things that exist in our atmosphere, and we don't put much resources to resolve them. For example, acoustic waves, sound waves, they are much faster. You can see that they could be in very large scale in space, but very short time scale, right? So they're very fast. And for the molecular diffusion, so things happening very close to the surface, to the solid surface, right? They are molecular diffusion. So the things that we actually care about are in between here. So looking at this graph, we know how we get rid of the things that we don't want, especially the faster waves. Why do we want to get rid of the faster waves? They're faster, right? They possess higher energy. We don't want the signal coming from the sound waves to overlap or just override the signals that we have in here, right? If they're larger, they're larger in magnitude, then they kind of like overshadow the things that we have. Okay, so the ratio here, the spatial and the time, the spatial and the time scale here, the ratio, they represent velocity, and they also represent the kinetic energy, right? V squared. Okay, so the governing equations that we talked about last time, they support many wave-like solutions. So these are the waves that we want to resolve. So there are different ways to do assumptions, and in abstract science, most of the times we use different ways to represent density, right? How we represent density is related to how complicated the models are. Okay, so very, very simple way to separate them. The first one would be incompressible atmosphere. Okay, so the total change is 0. And another way to do modeling is an elastic approximation. So why do we do this? So density is changing over height only. It doesn't change over time or doesn't change over space horizontally, because this is the dimension that density changes the most, right? Okay, so the first one is the incompressible atmosphere. This is the first assumption that we make. So in the continuity equation, we just cross out this one. So we know that we have the mass conservation becomes volume conservation because the density doesn't change. Okay, so there are different conditions to fulfill this. The first one is that the square of the wind speed. So this is representing the weather system that we have in the atmosphere, the speed, the general scale of the speed. So we talked about this, right, in this graph. So they have like a general speed for different things in the atmosphere that we care about. So this should be much smaller comparing to the sound speed. Okay, and this is fulfilled because this criteria is fulfilled actually. So, and the second one is the characteristic time scale. So or you can think of it as the oscillation time or the period of the waves that you're looking at should be much larger than the time scale changes due to sound wave propagation. So this is also met in the atmosphere, so you can compare the time scale of the weather systems and the time scale of the sound waves in here, right? And the third one, so this C is very much related to what you make in here, the assumption that you make in here, right? For the density to not change to not change. Okay, so the vertical scale of your circulation, the circulation of your weather system, should be much smaller than the scale height of the atmosphere. I hope you have learned this scale height. So this is like an index measuring how thick the atmosphere is. It's not an actual height of anything, but this is like an index. So for example, if you have some convection in the atmosphere, the height of the convection should be much smaller, or the horizontal scale. Oh, no, this is just vertical scale. So the height of your convection should be much smaller comparing to the scale height of the atmosphere, which means that the things that you're looking at should stick near to the ground, very close to the ground, not like deep convection. Okay. So I hope you have got some paper with you. You can see this one. Okay, so the first one is compressible. The total change of density is 0, and the conditions is that the wind speed of your weather system is much less than the sound speed. And also the vertical scale of the system is much smaller than the scale height. So which means that whatever the things that you're looking at, it should stick to the ground, right? Small scale height. Small vertical scale. Okay, so this is the horizontal dimension, and why do we stick to the ground? Because we want the density to be constant, right? Okay, so we do scale analysis. So For those of you who haven't heard about scale analysis, it is the study of the order of different terms so that we can get rid of the smaller terms, of course. Why do we do that? Right? So this is the vector form of the momentum equation. Right? I have that in the next slide. Okay, so how do we turn this momentum equations into vector form? The first term on the left is advection, so the change due to movement. And the second one is we assume that steady state, so we cross out the local change. Okay, local change here, we cross out that. And then this one is just the pressure gradient force in vector term. And the third one is due to this gravity. Okay, and we assume that we don't have Earth rotation. Of course, it's not true, right? But this is like a simplified model. So we cross out these. So what are left is advection, pressure gradient force, and gravity, right? You don't need to, this is not in the midterm or exam, don't worry about that. Okay, so I'm just showing you how we do scale analysis. So we have three terms now. First one, 1, 2, 3. So the scale. So now we do the scales. So the scales here, the first one is v squared. So the order of wind speed is the same as the change, the order of the change of the wind speed. Okay, so that is v squared. And then this one is, of course, is 1 over rho. Okay, and the change of pressure delta rho. So the change of the pressure, we assume that is coming from sound waves only here. Okay, so the divergence. So this is the divergence of pressure. And the corresponding density variation. So this is the density variation. So CS is the wind speed of sound waves. Okay. And this one is nice. The change of your geopotential height is close to 0 because we have like very shallow circulation, right? Okay, so now what we have left is change of density over density, which is 10 to the power minus 3, almost 0. And this means D. It means order of. Okay, so the first criteria is met when we compare the wind speed. Or you can just look at the graph that I showed you, the spectrum that I've shown you. If you can't see the screen, you can type into the Zoom meeting. 讲得很容易。I'll give you 30 more seconds. Any questions? Hi.
Explain again the rationale of doing this scale analysis.
This is just showing you why we can't get rid of the sound waves. And you can actually see the, guess the mean speed from this spectrum, right? So so this is almost zero, right? We do this comparison, this is almost zero. So the density variation due to sound waves is very, very, very small. That's the rationale behind this. And we can basically ignore that. Okay. Okay. Okay, so I think I have explained this. We're just redoing this slide actually. What I've just shown you, you can look at the slide. Okay. So this is for your information for reference only. So the next one is an elastic approximation. So, okay, so now we're not happy because we are only having the representation of very shallow air, right? Here, very shallow air. It's not good enough, right? And density is constant. It's not good enough. We know that the atmosphere is thinner and thinner when we go up, right? So the density variation vertically in the atmosphere it could be large. So we want to have that representation, but we want to leave the sound waves out. So how do we do that? We do this an elastic approximation. So we allow the density variation with height, this one. So now you have like a profile of your density over height, and it stays the same over time, and it stays the same over space or horizontal space. Okay. So the second one is an elastic approximation. So we now one step forward to make your model a little bit more complicated. Okay, so what does it look like? Oh, sorry. One to hang out. Okay, so this is the profile that we have. Okay, now if we do, so it doesn't change over time and it doesn't change over horizontal space, right? It only changes with height. Okay. So the dimension here, they don't matter. Okay. So the trick in making or an abstract model to be more complicated is to work on the density. So now we have the continuity equation, and this is the wind speed. So the change, this is the first term is local change, and the second term is the change due to movement. Right? And we know that this is 0 because this is what we assume, right? This is the setup of our model. We assume that doesn't change over time. So now we can rewrite this. And we can further rewrite this one. Okay, you should be able to do it on your own, but I'll just write everything out for you. Okay, so you can see that we have something extra in here because of the setup we have. Oh. Okay, then next we need to work on the scale analysis. Okay, so this is how we arrive at the equation in here, and you can see that from the textbook. Okay, I have the link here, and that addition is what I used when I was an undergraduate. So if you want a newer version, just you can find it on your own. Okay. Okay, so next we work on the scale analysis on continuity equation. So how do we do the scale analysis? Would you have a- Okay, so now so we're not happy that we only have the representation. The variation, we are not happy. Okay. We only have this, right? The change of density over height. So we're not happy. So we want something that could represent a very small change of density. So now we separate the total term, the density, into two parts. The first part is what we have just discussed, right? The vertical change. And the second part, we call this the perturbation. Usually we ignore this one because this is dominated by this one. So we usually ignore that, but so don't worry about that. So we have separated the density change into two parts. Of course, the first part is much larger, but the second part, you don't want to ignore that either. So this prime term, sometimes, sorry. Okay, so I'm not drawing it anymore. Okay, that's the changing part. That's the part you want to allow changes. This is a changing part, right? Why do we separate the two terms? So there are many reasons. Usually scales are not, it's not easy to separate that because things are overlapping in the spectrum. The spectrum meaning meaning the graph actually. Okay, usually they overlap, which means the energy overlap, which means that you cannot separate things. They're not linear, but sometimes we can see very clear separation of energy in the spectrum, and we know. Okay. Well, we could separate them. So this is how we separate them. So we like to think of this one as the large scale circulation, representing the mean over time and space, or the large scale circulation. Or coming from large scale stuff, global scale. Okay. Okay, so now we know that this is not zero, and this is not zero, right? The perturbation, the change of the perturbation over horizontal space. This is also not zero, and it changes over time, right? Okay, so the continuity equation again. This is the big D, total derivatives. Okay, this is just the same lecture one. Same as the one that I've just shown you, the local change. Right? This is local change. This is change due to movement. Okay, just the same. So now, why do I write this again? I want to substitute this one into the equation. Substitute this one in here. Okay, if you're able to read the textbook, you can just skip this lesson and do it on your own. I've put down the linking in the slide. Okay. rho naught is changing over vertical dimension. So we can still see it in here. Okay. So now we do, oh, so this is, so we know that rho naught is much larger than rho prime. So approximation again. This will not be in the midterm or exam, don't worry about this. Okay. So now we do the scale analysis. For the synoptic scale, around 1,000 kilometers. This is 10 to the power minus 7, and this one is 10 to the power minus 6, 10 to the power minus 6. Okay, which means that we can ignore this term. So anything less than 1/10 or something else, we ignore that. That's like a common practice in atmospheric science. Okay, we ignore them. So what is the implication of this? Even if you introduce the density perturbation, it would be too small to be noticed in the synoptic scale motion. That's the implication, which means that it's not necessary to include the rho pi in your model if you're talking about synoptic scale weather systems. Okay, 我寫出嚟啦。Okay, it's all in the textbook. You have the link here, yes. Okay, I have just done the same thing on this slide. So if you miss anything, don't worry about that. It's in here. I just didn't put the graph in here. Okay, no graph, but you get the idea. So it means that we can rewrite the equation. I'm sorry, we still don't have programming exercise this week. Maybe 1 to 2 weeks later. Next week. Okay, so we can. This is what you see sometimes in different approximate models. So this one works for synoptic scale weather systems. Okay. Okay, so I think you probably have seen this many times. So this is what we mean by synoptic scale system. At least 1,000 kilometers in the, of course, in the horizontal scale. Okay. At least 1,000. So, for example, cyclones, or these are mid-latitude cyclones, hurricanes. So you can see the size, right? This is this is United States, so you know the size. So things which are larger, they are called global scale. For example, Hadley circulation, or smaller things, mesoscales, thunderstorm, tornadoes. So this is like a summary for the things that we have just talked about. So the incompressible atmosphere, of course, it should be just for the shallow circulation, so stays near the ground or for a certain level only. Okay, and if you want to extend your knowledge to higher levels, you want to include the density variation vertical variation into your model, you can choose this anelastic approximation. So this is how we handle density in different abstract models. So the more variation you introduce to your model, the more complicated your model is. Okay, so this is the vertical momentum equation, right? This is like the simplified vertical momentum equation. Why is it simplified? Because this is balance, right? It's not describing the change over time. So what would be the original vertical momentum equation be looking like? I think you all have seen this, right? Huh? The map from Gadget. Okay. Of course, we developed this from the very first Newton law, right? But we changed that coordinate system to the coordinate system we have on Earth. So this is what it looks like. The change of the vertical motion over time, right? So what is hydrostatic approximation? We cross out different terms. So this one. So the change is zero, basically. The change over time or the change due to movement is zero. And also other terms meaning the friction or Coriolis force in the vertical dimension, they're gone because they're too small. So that's why we have the two terms left, right? So that it's hydrostatically balanced. And the thing is that if we again separate the P, the pressure, again into, we can do the same trick, right? The change of pressure over the vertical dimension and also other perturbation. Same as density, okay? If we do this, hydrostatic approximation only works if the perturbation part also is hydrostatically balanced. Okay, so this only works if, oh, sorry, this is P. So this is horizontally. Why do we care about this? Horizontally varying pressure gradient force, right? it could be, right? If you put P prime back to the horizontal momentum equation. And this one also horizontally. Alien density change. They should be balanced. Right? Since this one is not zero, it will appear in the horizontal momentum equations, and we care about that too. Okay, so the scalar analysis is in the textbook, is out of the scope of this course, actually. I just want to include that because that's important. For more, please see Holden 2.1, section 2.4.3. Okay, they've done the scalar analysis for that too. Okay, I have the link in here. Yes. Okay, I think we should take a break. Okay, for 10 minutes. Okay, thank you. Okay, so let's continue. Next, we have this. Okay, I've explained it. So next, I want to introduce to you the Boussinesq approximation, which is like the very common approximation that we have. And if you open the textbook, they put this in the chapter of boundary layer meteorology. Why do they put that in boundary layer meteorology? This is not necessarily for boundary layer meteorology, because this is talking about shallow circulation. So shallow circulation, which means that it's things that are sticking near to the ground, which is the boundary layer, right? So it's not necessarily for boundary layer. So the trick here, so the trick that we have just talked about is the things that we do in the continuity equation, right? Continuity equation. So the change of density, we work on the equation for the change of density only, right? But for the Boussinesq approximation, we want to introduce the density variation further. We want to introduce the density variation in the momentum equation, because if density is changing drastically, it could induce some buoyancy effect. Buoyancy meaning buoyancy due to gravity, right? We're standing on the earth, we have gravity. So which means that we need to do the trick in the vertical momentum equation. So we can see that the gravity is adjusted here. So it's called the reduced gravity. So so this slide is explaining why do we have the reduced gravity, because we separate the pressure into two terms again. Okay, the graph here is supposed to show you the separation, right? We have the pressure change over height, right, which is the largest one. Why do we separate this? Because this is the largest one, the largest variation, and then the pressure perturbation. So you can think of this as the hydrostatically balanced component, first one, right? So this one is coming from the environment, P naught. And this one is the pressure perturbation, which is due to your weather system. Okay, separate them into two terms. And this one will act as the buoyancy, because this is coming from the environment, right? Buoyancy is the force that your environment is pushing you, okay? So we change that to the buoyancy force. Okay, this line is also optional. So anything I put in gray in here is optional. So the gravity now is reduced because of this, the buoyancy effect coming from the environment. The environment is giving you something, okay? And it was also very confusing for me as an undergraduate student, because the P that they put in the textbook, they don't have the special sign in here. They just put the original P in here, which is very confusing, I think. So if you open the textbook, that's what you find. But remember to understand the whole thing from the original momentum equation in here. Okay, so I have the link here. So this is the trick that we have done to the horizontal or the vertical momentum equation. I can show you some graphs. Okay, title. Okay, so this is the sorry. Okay, so this is the shadow layer. So rho is constant because it's shallow layer, right? And hence we have this incompressible continuity equation. So your density variation only appears in the terms dealing with gravity. Why do we put it? Why do we have this arrangement? Because gravity is a large term in the vertical momentum equation, is around the order of 10, right? Since P is large. It's not 10, but it's the order of that is around 10. Okay. So if you measure anything in the real environment, in the real world, if you measure anything, the vertical motion is a very, very small term, right? The gravity is large, gravity is like 10. So if you measure the vertical motion in the atmosphere, you can find that sometimes it's often 0, right? So if you have something this small and then you have 10 in your equation, then your gravity is going to dominate the whole motion, which means that even if your density variation is very, very small, and when you do the multiplication, then your term is not small, right, due to buoyancy. So you cannot just ignore the density variation, right? So if we blow this up, we have the air moving vertically. This is just explaining this is just explaining the concept of buoyancy, just some basic physics. Okay. Okay, so we have some air in here, and the pressure here is P naught. It's the same air, so the pressure gradient coming from the environment is the buoyancy force. Okay, so So now if you have some changes to your pressure, we have the arrows, which is the buoyancy force. And then you have the perturbation, which is coming from your weather system. Okay, maybe you have latent heat, maybe you have, I don't know, some water freezing, okay, in the atmosphere. So you have the effect of the buoyancy force and then the perturbation. Okay. Okay. So we only have the density variation, which is this term, introduced in your vertical momentum equation. We have gravity in here. We don't have gravity in the horizontal momentum equation. Okay. So this is like a summary of different filter models. Okay, so the simplest one that we have here is the homogeneous density one, which is this one. So incompressible, your atmosphere is incompressible, which is only applicable to shallow layer of circulation. Okay, and the next one is Boussinesq approximation. So we can still have incompressible atmosphere, which means that we are sticking to the ground. We are very close to the ground, but we care about the density variation, which is causing you buoyancy. Okay, we care about that. So we introduce something, a little bit something more. So this is a little bit more complicated comparing to this one. And then the next one is the inelastic approximation. We have just talked about this. So this is for this model, deeper convection or deeper weather system is allowed. Or you can have the fully compressible, which is the original continuity equation. Okay. Any questions? Okay, so we have 7 primitive equations, right? We have the momentum equations in 3 dimensions and then continuity equation. And this one is the continuity for moisture. Q is the mixing ratio, I think, of specific humidity, sorry. Okay, and then the thermodynamic equation and equation of state. So 7 primitive equations, 7 dependent variables. So these are the dependent variables, the ones in orange. Okay, so we can choose other dependent variables instead of these for the sake of modeling. Okay, so we can replace different things. So this one is much more complicated. I'm skipping this. So we can, the example is that we can replace P pressure by pi. So you will have to do this for the exercise. So pi is actually, it can be, it's defined, actually it's defined like this. So it's representing the pressure. And then we have the surface pressure here also. Okay, so we can rewrite the 3 momentum equations with the new dependent variable in here. Okay, I'm not going further. You have to work on this for your exercise. So why do we do that? So in here, you can see that you have got written of density, which is which could be very messy. We don't want that in our equation, so we change that to this potential temperature. And the vertical gradients of pi is much less than the vertical gradients of P. So it all comes back to how large your variables are, or how fast your variable is changing, right? Because this one is changing much slower or much less comparing to the change of P in the vertical dimension, in the vertical sense. Okay, this is changing less, which means that the precision that you need to calculate that is lower, or you don't need as much precision. By precision, I'm talking about the digits in your computer. Okay, if this is changing less, then you might have a better representation in your computer, right? So in our model simulation, we always avoid very, very small terms, very, very small numbers, or very, very large numbers, because we lack the representation for that. Because okay, willing or not, you will have to do some truncation in your numbers. You have to truncate some digits because resources are limited, right? So you don't have enough resources to represent everything and over all the space all the time, right? So even for one number, you don't have the precision to represent everything. So you have to truncate some of the digits. So that's why you want your number not to be too large or too small. So the vertical gradient of this one is much less, so we choose this over pressure. Okay, after you have done the calculation, you can always change this pi back to pressure when you need to plot that on a graph. Okay, so we want to avoid steep changes or fast changes. So this is the reason to use this X-ner function. Okay, so next we talk about coordinates. So we are simulating things not on a perfectly flat surface, right? We are simulating things on the globe or inside the globe. Okay, so not regularly shaped stuff. So you can see that in the global model, we just cut the atmosphere into different parts, right? And the problem is that you can see that for some of the boxes, they are smaller. They're not representing the same area actually. So it's not perfect. So we need to work on the coordinate system. We might have to face some distortion sometimes. Okay, so next we talk about map projections. This is not a numerical method, so this is needed in Earth system modeling. So we have different coordinate system, right? The longitude, latitude. I hope you know what they are, right? Longitude and latitude, and the vertical distance from the surface, or this is okay from the surface. Okay, so I want to show you this video.
丹麥藍罐曲奇係值得你屋企嗰位女王享有嘅。
咦，係咪要駁聲啊？我想問。要駁線喺呢度。Okay, never mind. Okay, never mind. Maybe you go back and watch it. So it's just showing you there's no way to project things. No way to project things on a sphere onto a 2D surface perfectly. By perfectly, we mean that there's no way to do it without distortion. Okay. It's fun. Please go back and watch it. Okay. Okay, by projection, we are talking about values, for example, here on the globe. We put that back to a paper, to a piece of paper. A piece of paper is 2D, right? This is 3D. So if you put the numbers back, each of them back to the 2D surface like this one, cylindrical. This map projection is called Mercator. So there is some problem with it because if you use this one, there would be so the area your map representing in the equatorial area is not the same as the area because this is on a globe, right? You can see that this box should be much smaller comparing to the box near the equatorial region. Okay. And also, okay, if you use different piece of paper, for example, if you use this one, the conical one, and you project things from the Earth surface to this piece of paper, you will also face some distortion, okay? Except the place where your paper is touching the slope. Okay, also the same for this one. If you look at the Earth from the top view, then you have like a map for the, I don't know, North Pole or South Pole, okay? Then you will also have some distortion except for the place where your paper is touching the slope. Okay, so if you put your paper, for example, this piece of paper, and then your piece of paper, your cylindrical piece of paper is touching the slope at two locations. It's not a solid sphere, okay, an imaginary sphere. So you put that around this cylindrical, put this cylindrical paper around this globe, and it's touching over 2 points in here. So these 2 points are these 2 lines are the locations where you don't have distortion. So they have the same ratio comparing to what you have in reality. You can also do the same for this different map projection. For example, this one, Lambert conformal. These are what you can actually see in the atmospheric model if you are asked to do model simulation, or this one. Okay, so we have the representation of this distortion. It's called map scale factor. So it's the distance on the grid over the distance on Earth. For example, this one, Mercator projection, we project things. So this is how we project things, right, for each of the latitude. So the true latitude here, which is the place, the locations where you don't have distortion, is 0. It can be in other places, right? It can be in 20 degree north and south, but for this one, it's 0. This is the world map that you usually see. So no distortion at the equator only. So it's suitable for the tropics. So that's why for Hong Kong, maybe people like to use Mercator projection when they do abstract modeling. Okay, and the map scale factor is calculated like that. So the distance on the grid over distance on Earth. So the mathematical way to calculate that is like this: distance on grid, radius at the true latitude, and then distance on Earth, radius of the location. Here, this is how we calculate radius of the location. This is like the ratio. This is not the radius of the location. Okay, the ratio between these two. Okay, so next we talk about vertical coordinates. It's a little bit tricky because sometimes you see height. Actually, there's no time you see height in abstract modeling. We don't use height. It's more convenient to represent the vertical dimension with pressure, actually. And so for the pressure coordinates, you have to reverse things because in the Z coordinate, you go up and the height increase, right? For the pressure, it's the pressure increases when you go down. So it's the reverse. So W is representing the vertical motion in the Z coordinate. So positive is upward. And for this omega, which is the vertical motion for the pressure coordinate, if it's negative, it means it's going up because if you go up, the pressure decreases. Okay, we need to rewrite the governing equations with the new coordinates. So for the pressure coordinates, how do we do the conversion? By conversion, we are talking about the vertical motion here for the vertical motion, which means how do we convert this one W to omega? So we apply the chain rule to the vertical motion in here, W in here, which is the change of the vertical location over time, like the total change, sorry, the total derivative. And then we do the chain rule. Don't worry about this, this will not be in the exam or midterm. So I'm just showing you how we do the conversion. So the goal here is to do the conversion between these two, the vertical motion, W and omega. So we expand this W into different terms. So for this one, this is the total change, right? This is just U, total change of X location, right? So this is the U. So the change due to affection, actually, the change due to movement. And also for the other dimension, horizontal dimension. Okay, and then this one is what we actually want, the change of the pressure, total change of the pressure, which is omega, right? So this is how we relate this omega with the original vertical motion W. Okay, and then we get rid of the rest of them, they're negligible, very small. So these are the slopes of your pressure surface. Why are they the slopes? So if you walk in the vertical distance, this is the change of your height. Okay, so if you have a slope, then you have something in here. But usually pressure is rather flat, right? Pressure surfaces, they're rather flat. So that's why they're negligible in here. And this is the vertical motion of your P surface. Usually they don't change much in the atmosphere unless you have something very vigorous. Okay, they're very small. So in atmospheric science, we always do this cross out terms. Okay, so next, so we have dealt with the vertical motion. So we also need a set of new derivatives for your pressure coordinates. They will not be looking the same. By the vertical and horizontal derivatives, they are here. This is horizontal, right? These two. So we want the total change. We want to rewrite the total change in terms of different things, and the vertical dimension should be in P, right? It's not in Z or it's in C anymore. So this is the goal. We want to rewrite this. We want to rewrite this, relate them. We want to relate the vertical derivatives in here, right? So just rewrite things, chain rule. Okay, and this one is coming from the this is coming from the hydrostatic equation, right? Okay, so very easy. This one vertical derivative, and the horizontal derivative is also very easy. We apply the chain rule. So we do the conversion between these two. So the goal here, originally we see this, right, in your momentum equation, and you want to have the change over P surface only, not the C surface. Okay, let's say you have a variable, any variable, and you apply chain rule. I hope this is not too easy for you. Okay, apply chain rule. And this is keeping Z constant. This is keeping X constant. Okay. And we want to look at the change of A with X on pressure surfaces. So very simple. So this is constant P, right? Because it's on P surfaces. Again, this is just repeating. This is also repeating. Okay. On P surface, right? We are talking about changes on pressure surfaces. So this is the pressure coordinates, right? And this is the Z coordinate. Horizontal derivatives. So okay, so we have this originally, right? On the C surface. Now we want this. We want this. So we are basically, this is what we used to calculate. Now we want this, right? The change horizontally on P surfaces. Okay, so this is how we arrive at what we see on the slide. So the thing here is that you cannot just, they're not equal apparently, right? There's something else in the equation. So the something else, what are they? So this one is just one. You can see them. It's just one. So what are the things, what are the extra things you need if you do the conversion? The first one is this one, right? The vertical change. So now when you want to change the coordinate system, it's complicated because you also need the vertical stuff, the vertical change. Even if you're calculating horizontal derivatives, the change, vertical change of variable, right? Partial A, partial Z, okay? And then also, the second thing you need is the slope of the P surface. This is the slope, right? If you go horizontally, then if you're going up or if you're going down, then there is something here. Right? It's the slope, which means that if your P surfaces they have some ups and downs, then you need to care about that in the horizontal derivative. Okay. Actually, if you do modeling research, you don't need to care about that because this is all taken care of by the model. I mean, if you can be a student from computer science and handle the model, because this is written by the scientists already, right? You don't need to care about that. Okay, so this is how we convert the horizontal derivative on Z surface to the horizontal derivative on P surface. Okay, so why do we do that? Because if you use Z surfaces, which is the actual height, so these are the actual heights, right? If you have some topography, then you will have like disasters happening when your sea level is touching the ground, right? You have to have very complicated problem, complicates the formulating in the Boundary boundary. Okay, this is undesirable, so that's why we need P surfaces. Actually, P surfaces also intersect with the ground, because if you go higher, then the pressure is not the same, right, as the surface. So the ideal vertical coordinate is to follow the domain and no intersections, right? And that's why we come up with another coordinate system, which is called the sigma pressure coordinate system, or we just call it sigma. Okay, so this is the sigma coordinate system. So there are different levels in here, and the sigma levels, you can see that it's spanning from 0 to 1. 1 is representing the model surface, 0 is representing the model top. You always have a model top, even though your atmosphere is extend to, in theory, the infinity, right? So the pressure here is constant PT, and also the pressure in the surface is also constant, but it's changing horizontally, right? It's depending on X and Y. So you need to have like a defined surface pressure profile for your model if you use this sigma coordinate system. So this one is already predefined. The green one here, also the red ones, they are predefined. They should be predefined, okay? And okay, and this is how you calculate the sigma level. So basically, you turn this pressure into the reference, the sigma variable. And we have to define the new vertical velocity, which is the change of the sigma along your motion, right? So it's just very simple. And we can do the same for the vertical velocity. We have just done that for the pressure coordinate, right? So it's the same, very similar. Vertical velocity and also vertical or horizontal derivatives. It's very, very similar. So I'm not redoing that in here. All right, let's think that okay, very quickly. So let's say if you have some topography in here. And you want to look at this location A. So this is the height, D1, and you have the predefined pressure, the pressure of the surface predefined. So you have the pressure top And you have the vertical profile for the pressure. So the surface here is height surfaces, but you have like profile for the round here. Okay, so this is P naught minus PT. And this is PS minus PT. So the sigma will be just the ratio. So that's why it doesn't have a unit. Right? So it's the ratio between the two terms. The fraction of the pressure differences. From top to bottom. This is how we define the sigma surface. Okay. This is just repeating what we have on the slide again. Okay, I'm just showing you something to explain more. Okay, so in the model, this is what we have, the surface pressure. So it's in terms of X and Y. And it's all, of course, it's depending on the topography that we have and also atmospheric condition that we have. So in the very high mountains, the pressure is lower, right? So there are different advantages of having the sigma coordinates. So it's relatively simple and easy to handle, to program, and they have smooth representation of bottom topography, right? We don't have to drop sand, we don't have to bump into the mountains, right? And they allow concentration of coordinate lines in boundary layers. So by boundary layers, we're talking about the layers closer to the surface. And we allow more representation near the ground because we need that. 50% of the atmosphere is actually near the ground, right? That's why we need more representation for that. And the disadvantage is that if we have very steep mountains, then you might end up having some errors, having some misrepresentation in your equations, because we have just talked about this, right? The slope of your surfaces could be contributing to different terms in your horizontal derivatives, right? We don't want that. Okay. And vertical separation between two sigma levels. So the sigma levels are depending on pressure, so they don't represent the same distance, right? Of course. And the influence of topography are present in the upper level. So you can see that the mountains may have some influence in the lower layer of the atmosphere, but if you use the sigma levels, you will have something in the even higher levels, which is not true in the reality. Right, this is one of the disadvantages. Okay, so I will give you some hints for the exercises. So this time we don't need to do coding again. Sorry about that. I know we hope to do that. For the first one, the first equation, the first question, you just do the conversion for this orange box. Right, you don't need to work on the whole momentum equation. Just do this conversion. Please start with the one on the right. Start with this one. Don't start with this one. It's much more complicated to work on this one. Start with the pi, the newly defined terms, and you need ideal gas law, right? P equals to rho RT. The R is the gas constant for dry air. And you will, of course, need the, or I already have it here, the potential temperature. This is the ideal gas law. You will need the equations. Also, the definition of this pi is in the slide. Okay, thank you. Really easy. And next one. Okay, you will need to show this one, show the horizontal pressure gradient force in P coordinates. So show that they are equivalent to each other. Please start with the left hand side. Okay, it's much easier to start with the left hand side, and you will need to use the horizontal derivative conversion that we have just talked about. Which is this one. Okay, we have just talked about this one. Use this one. And you already know the approximation. Okay. So the goal here is to do the conversion. So this term is the change of pressure on Z surfaces. So if you have a model which is working on this actual height as the vertical coordinates, then you need pressure to represent your different weather system, right? So this is the change, the pressure gradient, horizontal pressure gradient in Z surface. And then here, the horizontal pressure gradient in P surface should be represented by the geopotential height. Okay, so they are equivalent to each other. So how do we do the conversion? Okay. The third one is pretty easy. Just plug in all the numbers and calculate the sigma for each dot. Okay, the fourth one is probably the most difficult one. So you will need different things. Of course, you will need this one, this one that we have just talked about, the horizontal derivative for different coordinate system, right? And you expand this one first, of course, the left-hand side. And you will need different things. We need different things. Of course, you will need because you can see that there is the pressure perturbation, right? So you will, of course, you will need this one, right? Separate the pressure into two terms. And then you will need this one, the definition of geopotential heights actually, and also hydrostatic approximation. Because you can see that you have, okay, so in the end product or in the result, you have sigma in here. So you will also need to rewrite your P naught by the definition of sigma. Okay, I'm not writing that in here. It's very, very easy. Okay, so the question is asking you to explain when you do the coordinate system conversion. When your sigma surface becomes more tilted, the last term on the right, which is this one, Actually, these two will contaminate your result also, right? These two, but the question only asks you to explain this one. We introduce error in the pressure gradient force, the horizontal pressure gradient force. Okay, you will have to explain a little bit. You just have to explain this part. This part you don't need to care about. Although this also affects the horizontal pressure gradient force. Okay. And this one is optional. It's really optional. There's no points if you do it. Okay. I don't want to make it compulsory. If we have bonus points, then it's not bonus anymore. Okay. For this one, you will have to do some assumption. Okay, I have already given you assuming those. Okay. Okay, I think we Sorry. Okay, so the last question is about the problem of sigma coordinates. So this is what in the US, this is sometimes what happened. They have the Rocky Mountains, right? And then they have some cold air coming from high pressure system. And the cold air will stay behind this mountain. And the problem with the sigma coordinate is that if you have some air advection, your air advection will clear this cold air, which is not true in a reality because of the smooth surface around the topography. Okay. This is okay for the model in the point of view of the model. This is just zero gradient, right? This is following the surfaces, right? This is just following the flow, but that's not true in the atmosphere. So this is the problem of having sigma coordinate system, and this is related to the equation that we have from the question exercise 4. Okay, you have to keep here with, but this is just showing you already. Okay, so that's why people use another level. Yet we define another level, which is called eta level, which is supposed to solve the problem that we have in here. Okay, you don't need to care about this. I don't think anyone would want to type their homework with LaTeX. Okay, if you just added this course this week, you will have a different due time for homework 1. Okay, that's it. Any questions? 我通常都唔會教晒3個鐘，通常後面嗰個鐘用嚟做 exercise 嘅，不過你學有冇問題啊？要啊！啲同學喺度咁開心啊，其實對眼都識笑，好簡單。我都係其實功課，即係就係 lecture notes。係啊，嗰啲就係功課啦。即係唔係 Python 嗰嚿係關事啊？咩啊？我唔使嘅嗰個，我唔使嘅，嗰個我俾你練習下 Python。係。